Non-equilibrium phenomena in solutions, and in ionic solutions in particular, are observed when there is a non-zero gradient of some of their intensive parameters. Thus, for instance, if the temperature in the bulk of the solution is not constant throughout, the gradient of temperature will not be zero, and we speak of thermal diffusion. Also, if the pressure is not constant, then the gradient of pressure is not zero, and we speak of diffusion. We speak of diffusion also when the density of the solution is not constant throughout. Now, if the chemical potential has different values at different points of the solution, in other words, if the chemical potential is not equal throughout, then there will be a gradient of the chemical potential, which will give rise to the so-called molecular diffusion. And now, because the chemical potential is a function of the activity of the ions, respectively of the concentration, then in such a case there will be a gradient of activity which will be different from zero. Respectively, there will be a non-zero gradient of the concentration. If the values of the electrical potential phi at different points of the solution differ from each other, in other words, if phi is not constant, then the gradient of the electrical potential will not be zero, and this will be the cause of a phenomenon known as electroconductivity. There are two things that need to be mentioned now. First, unlike the solid conductors observed in electrical engineering, where the carriers of electricity are electrons, or in other words, the current is due to the flow of electrons, in ionic solutions, the carriers of electricity are positive and negative ions. Thus, electrolytic solutions are considered electric conductors of the second type, or the second order. Second, because there are charged particles in the ionic solutions, when there is diffusion, there are two types of gradients that appear. On the one hand, concentration gradients, and on the other, gradients of the electrical potential. Thus, study of diffusion phenomena in ionic solutions is more complicated than in non-electrolytes. Now, the ions, being charged particles, can be the carriers of electricity. The relationship between the electrical potential, which is the cause for the motion of these ions, and the current, that is the coulombs per second, in the solution itself, is described by the so-called Ohm's law, where R is the resistance. Now, if the potential is expressed in volts and the current is expressed in amperes, then the resistance is expressed in ohms. This is the Ohm's law. When basic SI units are used, the resistance is expressed in kilograms times meters squared times seconds to the minus third times amperes to the minus second, because in SI system, volts are newtons times meters times coulombs to the minus first, and amperes are coulombs times seconds to the minus first. And if we substitute the volts and the amperes into the Ohm's law, we obtain, and because the newtons can be expressed as, we can substitute it here, which is equal to, however, we can now multiply by seconds to the minus second and divide by seconds to the minus second, and then this becomes amperes to the minus second, and finally we obtain which was to be demonstrated. The reciprocal of resistance is called electrical conductance, G, where G is measured in Siemens or ohms to the minus first, or sometimes in units called mH/O, the reverse of ohms. A word of caution is in order here. Thus, suppose we have the electrolytic cell depicted schematically here, then, although electrochemical systems of this type will be observed in more detail in another lecture, we will note here that the simple relationship between the potential, current, and the resistance, described by the Ohm's law, when constant current passes through an ionic solution, holds only for the bulk of the ionic solution, and not for the solid-liquid interface at the surface of the electrodes. Thus, if we have a way to measure the potential difference between 2 points in the bulk of the ionic solution, considering that the electric potential at one of these points is 0 for simplicity, and also the value of the current that passes through this ionic solution, then upon changing the voltage applied on the electrolytic cell, we will find out that the ratio between the measured potential and current will remain constant, equal to the resistance of the solution, characteristic of this solution. However, not only that the measurement of the mentioned parameters in the bulk of the solution is not an easy task, but more importantly, one of the main things that we want to know about an electrolytic cell is what is the value of the current passing through the cell when certain voltage is applied to it. And now if we plot the values of the current obtained upon the application of certain voltages on the cell and plot them on this graph, then the relationship between the potential and the current will be far from simple in most cases, and by no means can be described by the simple Ohm's law only. This relationship is usually presented with the potential as the abscissa and the current as the ordinate, because the current, or the rate of the electrochemical reaction, is a function of the applied voltage. As we can see from this graph, due to the polarization phenomena at the electrode surfaces, there's a region of potentials within which the observed current is much smaller than the current expected from the Ohm's law, until a voltage is reached, which is called the composition voltage, from which on the current increases steeply. Now this type of behavior, the connection between the applied voltage and the observed current in an electrochemical system, is the subject of study in an area called electrochemical kinetics, which we will talk about in another lecture. Here we will only mention that studying of conductivity in electrolytic solutions is done using alternating current of relatively high frequency, and this is done to avoid the mentioned polarization phenomena at the electrode surfaces. Electrical conductance can also be expressed as G equals kappa times S over L, where kappa is the so-called electrical conductivity, or the older term is specific conductivity. S is the surface area of the cross-section of the material through which the current flows, and L is the length of this conductor. Electrolytic conductivity, kappa, is the electrical conductance of a column of electrolyte of 1 meter length and a cross-sectional surface area, 1 square meter, or a column of electrolyte of a cubic form of 1 meter edge. The units in which kappa is expressed are omega to the minus first meters to the minus first. A quantity that better characterizes the solution, in the sense we're discussing now, is the so-called molar conductivity. This is the ratio between the electrolytic conductivity and the concentration of the solution. This lambda capital is expressed in omega to the minus first meters to the second moles to the minus first. Notice that the electrolytic conductivity of an ionic solution, kappa, depends on the number of ions in the solution. However, the number of ions in an ionic solution does not depend linearly on the concentration of the solution. Therefore, the electrolytic conductivity changes with the concentration and passes to a maximum as seen here from this figure. And from this figure we see that it is more expressed for solutions of sulfuric acid than for solutions of potassium hydroxide. And the least is the electrolytic conductivity for a solution of acetic acid. Therefore, the normalization of this electrolytic conductivity by dividing it by the concentration still doesn't yield a quantity of constant value. Here, in this figure, we see schematically depicted the variation of the molar conductivity with concentration in two typical cases, one of a strong electrolyte, potassium chloride, and another of a weak electrolyte, acetic acid. We see from the figure that in both cases the molar conductivity changes with concentration. However, in the case of a weak electrolyte, this change is more pronounced. Nevertheless, the very fact that there is a change of molar conductivity with concentration in the case of a strong electrolyte such as potassium chloride, and that at a nonlinear fashion, is very puzzling, because experimental evidence such as absorption spectra of strong electrolytes shows that these electrolytes are fully dissociated into ions when in solution. This posed a major problem with the Arrhenius' theory, and this and other questions will be observed in another lecture. We will only note that when molar conductivity is extrapolated to a value at concentration 0, this is called molar conductivity at infinite dilution, lambda 0. Another interesting fact regarding conductivity of ionic solutions is that each ion has its own individual independent contribution to the conductivity of the ionic solution. Thus, if we have solutions of these 4 electrolytes, of course, the molar conductivity will be different in each case. However, if we observe them more carefully, we see that in fact these are 2 pairs of solutions, each one having a common anion. It has been established that the difference between the molar conductivities in the first pair is exactly equal to the difference in the molar conductivities of the second pair. This means that the potassium and sodium cations have the same molar conductivities in all kinds of solutions, independent of what type of anion is present in these solutions. Thus, we may write that the molar conductivity, or the molar conductivity at infinite dilution, is equal to a sum of 2 terms. The first is the molar conductivity at infinite dilution of the cations, and the molar conductivity at infinite dilution of the anions. Another property that the ion displays in the presence of an electric field is the ionic mobility. Ionic mobility, U0, is the speed at which the ion moves under the action of a unit potential gradient. Here we will observe first univalent cations, the mobility of univalent cations. Let us observe a portion of the ionic solution in the form of a unit cube. And let the potential difference between the faces of this unit cube be phi. Also, the concentration of the cations within this unit cube, that is, the number of moles within the volume bound by this unit cube, be C plus, and the mobility of the cations, of one cation, be U0 plus. Then the product, U0 plus times phi, will be the speed of one cation under the action of phi gradients. Indeed, the ionic mobility U, as mentioned, is the speed of the ion under the action of a unity gradient, and phi is the number of gradients in this particular case. Indeed, the potential difference phi is the difference between the potential of the left face of the unit cube minus the potential of the right face of the unit cube over unit distance. Thus, we have potential difference over unit distance, which is exactly the potential gradient. On the other hand, this product represents also the distance that will be covered by this cation per unit time. In other words, if a cation resides at this distance from the cathode, per unit time it will reach the cathode. Now, the number of moles of cations residing at this distance from the cathode will be proportional to the concentration of these cations. In other words, this is the number of moles of cations that will reach the cathode per unit time. Or in our case, this is the number of cations within this volume of the unit cube that will reach the left face of the unit cube. Notice that for simplicity we have accepted the potentials of these two faces of the unit cube to be of positive sign. Now that we have the number of moles of cations reaching the cathode per unit time, or in our case reaching the left face of the unit cube per unit time, we can multiply this by the Faraday number F, which gives the quantity of electricity carried by 1 mole of univalent ions, cations in this case, or the number of coulombs carried by 1 mole of cations. So now in this way we have the number of coulombs, or the quantity of electricity reaching the cathode per unit time, or reaching the left face of our unit cube per unit time. But this is exactly the definition of electrical current. So this expression gives the electrical current in this case. We may divide the expression for the electric current by the potential difference phi, and this will give us the electrical conductance. As we already know, electrical conductance of an electrolyte of unity cross-sectional surface area and unit length is called electrolytic conductivity. Therefore, this is the expression of the electrolytic conductivity due to the cations in the solution in terms of their mobility. We can divide this expression by the concentration to obtain the molar conductivity. And we obtain the expression for the molar conductivity of the cation in terms of its mobility. Now, to finish this discussion, we'll observe what units the molar conductivity is expressed in. Because the units of the ionic mobility are meters per second over volts per meter. Indeed, these are the units of speed, and these are the units in the denominator of potential gradient, or we may write them in this way too. And the units in which the Faraday constant is expressed are coulombs or amperes times seconds per mole. We have, and amperes over volts gives omega to the minus first. We have finally. We will now move on to discuss another important property of the ions in solution when acted upon by an electric potential. Now we'll discuss the so-called transport numbers. Transport numbers are sometimes called transference numbers or migration numbers. Transport number is the fraction of the total current which is carried by a given ion in a solution. Now let us see what the quantitative expressions are for the transport numbers of the ions of a salt that ionizes into A moles of a cation of a valency Z plus and B moles of an anion of a valency Z minus. From the definition, the transport number of the cation is the partial current due to the cation over the total current, while the transport number of the anion is the partial current due to the anion over the total current. Now, if U0 plus is the mobility of the cations, then this expression gives the quantity of electricity that passes through a cross-sectional area in the solution per unit time under the influence of the electrical potential phi. However, this is exactly the definition of electric current. Therefore, this expression is the expression for the partial current due to the cations. A similar expression can be written for the anions, for the partial current of the anions. Now notice that these expressions for the current are similar to the expressions we already derived. However, we have generalized them here for polyvalent ions. Also, we can simplify them by substituting this. Now, we may substitute these expressions for the partial currents in the expressions for the transport numbers. Now, the electrical neutrality of the solution requires that AZ plus equals BZ minus, which leads to cancellations of these quantities in these expressions. Also, the Faraday constant may be cancelled out. And we obtain on the other hand, we may recall the already derived formulae for the molar conductivity of the cation and the anion, as well as the molar conductivity of the solution. And we may substitute these formulae in the expressions for the transport numbers. Now we can determine the values of these transport numbers T plus and T minus at several concentrations, and then by extrapolation we may find the values of these transport numbers corresponding to concentration 0 or corresponding to infinite dilution. And now, knowing the values of the transport numbers at infinite dilution and also the value of the molar conductivity of the solution at infinite dilution, we can find the molar conductivities of the cation and the anion. here we have the expressions for the molar conductivity at infinite dilution of the cation and the anion. It should be noted that once the molar conductivity of an electrolyte at infinite dilution is measured, and the molar conductivity of the anion in this electrolyte at infinite dilution is known from an independent measurement of another electrolyte of which this anion is a member, then the calculation of the molar conductivity of the cation at infinite dilution is straightforward. This is the difference between these two quantities. Also, once the molar conductivity is at infinite dilution of the cation and the anion of a weak electrolyte which we study are determined from independent measurements of strong electrolytes, then the molar conductivity at infinite dilution of the studied weak electrolyte is simply the sum of these molar conductivities of these two ions. This is very useful because, as we mentioned, the determination of the molar conductivity at infinite dilution of a weak electrolyte through extrapolation is quite unreliable. It should be obvious also that when we need to determine the molar conductivity of a solution of an insoluble salt at infinite dilution, as we know, direct determination of this quantity is quite inaccurate. Instead of the determination of the molar conductivities of the ions, we may proceed as follows. We may determine the molar conductivities at infinite dilution of several, 3 in this case, relevant solutions of strong electrolytes. And then due to the independent contribution of the molar conductivity of the ions to the molar conductivity of the solution, cancellations will take place here, and the value of the desired quantity is calculated. We'll discuss now 2 methods for an experimental determination of transference numbers or transport numbers. The first method is called Hittorf method. This is a schematic representation of one of the constructions of electrolytic cells used to determine transference numbers by the Hittorf method. As seen, this cell consists of 3 compartments: anodic, cathodic, and a middle compartment. This middle compartment is used to isolate the anodic from cathodic compartment, and yet it closes the electric circuit. Electrolytic cell is filled with the electrolyte, the transport numbers of whose ions are to be determined, and then current is passed through the system for a certain time. At that, the stopcocks of the middle compartment are left open. At the end of the experiment, the current is interrupted and these stopcocks are closed. Now the quantity of electricity that has passed through the system is determined coulometrically by measuring the weight of the cathode of the coulometer before and after the experiment, and also the change of the concentration of the electrolyte in the anodic and the cathodic compartments is determined titrimetrically. It will become clear shortly how we can use these changes in concentration of the electrolyte in the anodic and the cathodic compartment, as well as the number of Faradays that have passed through the system to determine the transference numbers, or the transport numbers. It should be noted that the current that passes through the system should not be too high to avoid heating of the system, which creates conditions for transport of the ions through convection. Also, the time period, the duration of the electrolysis, should not be too long to avoid transport of the ions through diffusion. Notice that in order for the results of this experiment to be accurate, the changes in the concentration of the electrolyte have to be contained only in the anodic and the cathodic compartments. Here's one concrete application of this method. As an anode, we may have a potassium mercury amalgam. The electrolyte is potassium chloride, and the cathode initially is mercury, and as the experiment progresses, it turns into potassium, mercury, amalgam also. After passing of 1 Faraday of electricity, or 1 mole of electricity, through the system, the following changes take place in the anodic and the cathodic compartment. In the anodic compartment, the anode itself loses 1 mole of potassium, which leads to the appearance of 1 mole of potassium ions in the anodic compartment. Also, because of the finite mobility of the potassium, the anodic compartment loses T plus moles, where T plus is less than 1, moles of potassium cations. Now, remember that potassium and chlorine are the 2 carriers of electricity in this case. And the fraction of the electricity, or this mole that has passed through the system due to the potassium, is equal to T plus, which is the transference, the transport number. Also, the anodic compartment gains T minus chlorine anions. Now T minus is the transport number, the transference number of the chlorine ions. In the cathodic compartment, the cathode itself gains 1 mole of potassium, which leads to the loss of 1 mole of potassium cations from the cathodic compartment. And again, due to the finite mobility of the ions, only T plus moles of potassium cations arrive in the cathodic compartment, and respectively T minus moles of chlorine anions are lost from the cathodic compartment. We may factor out the potassium cations here and here. However, from the definition of transference numbers, transport numbers, it follows that T plus plus T minus equals unity. Therefore, this expression in the brackets equals T minus, and we may combine these 2 terms to obtain. From this, we see that due to the passage of 1 Faraday of electricity through the system, the anodic compartment has gained T minus moles of potassium chloride, while the cathodic compartment has lost T minus moles of potassium chloride. Notice, however, that when 1 Faraday passes through the system, the anode loses exactly 1 mole of potassium, while the cathode gains 1 mole of potassium, which is in accordance with the Faraday's law. What is more important in our discussion here is that the changes of the concentration in the anodic and the cathodic compartments are proportional to the transference, transport number. Now, if we denote by VA the volume of the anodic compartment and VC the volume of the cathodic compartment, and also if we denote by C0 the initial concentration of the electrolyte, we may write, these are the expressions for the final concentration of potassium chloride in the anodic, respectively, the cathodic compartment. Indeed, in the numerator we have the increase, respectively the decrease, of the initial number of moles divided by the total volume of the anodic, respectively cathodic compartment. We may solve these expressions for T minus. And of course, if the number of Faradays that have passed through the system were not 1, but Z, we will have in these expressions the final concentrations Ca and Cc are determined titrimetrically. C0, VA, VC, and Z are known, and therefore we can determine the value of the transference number by substituting these values in either one of the expressions. The value of the transference number T plus can be obtained from the already mentioned condition that T plus plus T minus equals unity. Here's an interesting way to replace coulometry and to determine the transference numbers only titrimetrically. Thus, if we replace the potassium-mercury amalgam in the anodic compartment with a platinum electrode, we will have the following. The passing of 1 Faraday of electricity through the system will lead to the formation of 1/2 mole of chlorine gas, which will be evolved at the anode due to the reaction This will lead to the loss of 1 mole of chlorine anions in the anodic compartment. And again, due to the finite mobility of the ions, T plus moles of potassium cations will be lost, and T minus moles of chlorine anions will be gained in the anodic compartment. Here we have the same expression rewritten. We can rearrange it. We can factor out the chlorine anions. And we can substitute the expression in the brackets by minus T plus because of the condition T plus plus T minus equals unity. Which may also be written as, in other words, the passing of 1 Faraday of electricity through the anodic compartment leads to the loss of T plus moles of potassium chloride from the number of moles of potassium chloride that were already there at the beginning of the experiment. The change of the solution concentration in the cathodic compartment is the same as the change in the already observed variant of this experiment. Notice that here, both in the anodic and the cathodic compartment, there is a decrease in the concentration of potassium chloride proportional to the respective transport number. Now we may express the transport numbers T plus and T minus in a way similar to the variant of the experiment we already observed. Also, the meaning of the symbols here is preserved the same, and because T plus plus T minus is equal to unity, we may write from where, and we can substitute the obtained expression for Z in the expressions for the transport numbers. This only by a trimetric determination of the changes of the concentration in the anodic and the cathodic department. Without using a coulometer, we can determine the values of the transport numbers T plus and T minus. Now we're going to observe another method, the so-called method of the moving boundary, for the experimental determination of transport numbers. This is one variant of the moving boundary method, in which a glass tube is stoppered at one end with a metal, in this case cadmium, the transport number of whose ion is going to be determined. And this glass tube is filled with an electrolyte containing the salt of that ion, in this case cadmium chloride. And on top of that, another electrolyte is added, which is called indicator solution. And the important here that these two electrolytes have a common ion. The cadmium electrode serves as the anode, and a cathode is also attached. And when current is passed through this system, a clear boundary is seen formed between the two solutions. The best results are obtained when the two solutions have different colors, and also when the refractive index of the two solutions differs. When electric current flows through the system, this formed boundary moves upwards due to the following reason. First of all, notice that the mobility of the proton in the hydrochloric acid is higher than the mobility of the cadmium ion, the ion whose transport number we're studying. Also, the electrolytic conductivity of the cadmium chloride solution is lower than the electrolytic conductivity of the hydrochloric acid, which means that the ohmic drop of the cadmium chloride solution is greater than the ohmic drop in the hydrochloric acid, which means also that the potential gradient in the solution of cadmium chloride is greater than the potential gradient in the hydrochloric acid solution. This leads to the following. If during the movement of this boundary the cadmium ion happens to get ahead and fall into the region of the hydrochloric acid, then the lower potential gradient in the hydrochloric acid solution will slow it down. On the other hand, if the proton from the hydrochloric acid happens to lag behind and fall into the region of the cadmium chloride solution, then the higher potential gradient in the cadmium chloride solution will speed it up, and it will speed it up more than the cadmium ion, because the proton, as we mentioned, has a higher mobility. And this is how this boundary gets preserved in its motion upwards. Now, if Q is the quantity of electricity that has passed for a time tau through the system, that is, for the time for which the boundary has moved from its lower position to its upper position, that is, from position 1 to position 1 prime, then the product of Q and the transport number of the cadmium cations gives the quantity of electricity that was transferred only due to the cadmium cations. Then dividing this quantity of electricity by 2 times the Faraday number will give the number of moles of cadmium cations. And then we can divide it by the molarity of the cadmium chloride to obtain the volume which is occupied by these cadmium cations. And the volume, as seen here, is equal to the cross-sectional surface area of this glass tube times the distance which this boundary has moved at. And this distance we have denoted here by 1 prime. We can solve this equation for the transport number, and we can determine the value of the transport number of the cadmium cation T+ from this formula, where the quantity of electricity Q is determined colorimetrically, and the distance 1 prime at which the boundary had moved is determined from the experiment. Also, the cross-sectional area S, the molarity C, and the Faraday constant F are known. From the condition T++ T- equals unity, we can also determine the transport number of the anion. To obtain a good boundary, the concentrations of the studied and the indicator solutions have to be chosen so that the potential gradients in them exert equal force on the ions. Obviously, for an ion of a lower mobility, a higher gradient has to be created. Thus, the following relationship is determined empirically, where Tx and Ti are the transport numbers of the studied and the indicator ion, and Cx and Ci are their respective concentrations. We start with Ti over Ci equal to 0.5, or in cases when we determine the transport number of the proton or the hydroxide ion, this ratio is 0.8, and we carry out a preliminary determination of the value of Tx. Once we have found this value, then the ratio Ti over Ci is adjusted accordingly. This is one construction of a glass cell that can be used to study transport numbers by the moving boundary method. The right compartment and the tube are filled with the studied solution. On this central tube there are two marks. The distance between these two marks is determined precisely, as well as the diameter, respectively the cross-section of this central tube. Upper part of the tube is closed by a small rubber cap. Then the left compartment and this vessel are filled with the indicator solution. When the current is turned on, this rubber cap is lifted slowly, and the time for the passage of the boundary between the upper and the lower mark is determined, as well as the other parameters as already discussed. We should mention here that there is a variant of the moving boundary method in which coulometry can be avoided. In this method, instead of one, two indicator electrolytes are used. The gradual change of the conductance of an ionic solution when portions of another electrolytic solution are added to it, causing the formation of a product of a low ionization constant, can be used for the so-called conductometric titration. We see that with each addition of the titrant, a corresponding portion of the cation A+ is replaced by the cation C+. Indeed, we see that this portion of A+ is bound into the product AD and does not exist as an ion anymore in the solution. However, the contribution of the cation C+ to the conductance of the solution differs from the contribution of the cation A+, and thus while the concentration of the Ni&B- remains the same during the addition of the titrant, the ever-increasing concentration of the C+ causes the overall conductance of the solution to change accordingly. In this concrete example of titration of hydrochloric acid with sodium hydroxide, the replacement of the rapidly moving protons with the slowly moving sodium cations leads to the decrease of the conductance of the solution, and it attains its lowest value at the endpoint. After the endpoint, the conductance again increases due to the increased concentration of the sodium and especially of the increased concentration of the hydroxide ion due to the addition of the titrant. Notice that conductance is multiplied by a correction factor where V0 is the initial volume while V is the volume of the added titrant. Conductance changes linearly with concentration. However, what is more interesting and important here is that the endpoint of titration is at the crossing point of the extrapolated best fitting lines drawn through experimental points away from the endpoint. This is important because in some cases, at the endpoint, the reactions may not go to completion. For instance, when titrating weak acids and weak bases, or when during the titration slightly soluble salt is obtained. In such instances, the values of conductance around the endpoint will not be useful for the purposes of titration, because in this region, a curvature in the plot is observed. Because the concentration of the species that are being titrated decreases around the endpoint, the ionization constants of weak acids and bases, as well as solubilities of slightly soluble salts, increase, which affects the conductivity of the solution. This is approximately the form of the titration curve from the conductometric titration of a weak acid, acetic acid, with sodium hydroxide. At the beginning, as expected, the conductance of the solution decreases due to the replacement of the protons with the sodium cations. An additional decrease in conductance is observed also due to the appearance of free acetate ions. These free acetate ions cause a suppression of the ionization of the acetic acid. However, as the concentration of the free acetate ions increases, these ions, together with the sodium cations, cause the increase of the conductance of the solution. This compensates for the initial decrease in the conductance, and a minimum in the titration curve is observed, which has nothing to do with an endpoint. At the endpoint, the actual conductance data belong to this curved part of the plot. However, this does not affect the assessment of the endpoint, because the endpoint is found by extrapolation of the linear parts of the titration curve. This curvature in the plot is due, as already mentioned, to the hydrolysis of the produced salt at the endpoint, in this case of the sodium acetate produced at the endpoint.